Everybody for joining us. I am Mike Rayleigh. I am PAC International's Director of Engineering, and with me today I have Ben Schaefer, who is, what are your like acoustical technical services manager or something like that? I always forget your exact title, but he's the acoustics guy for PABCO.
Yeah.
He manages all of their acoustical testing and does with technical support for acoustics and a lot of other things for PABCO. So, Ben, thanks for joining us. And
Yeah. Thanks for having me.
yeah, it's always a pleasure to have you. And a lot of the data in here, as we'll talk about, a lot of it is stuff that Ben has tested, and then there's other stuff that we've tested together. So the presentation we're going to do today is a bit of a repeat of the ASA presentation we gave a little while back. But since we're in this webinar format, we have a lot more time. We've got time to open it up for conversation with people, let people chime in, have some discussion. And we also have some new data at the end of this to share with you some new stuff that Ben has done. And just a reminder as we get going here. So I've allowed everybody to unmute so that we can have some discussion. But if we're not in the discussion portion, or if you're not talking, if you could please mute your mics. That way we don't have background noise interfering. That would be great. And we are recording this, and we will post it to our webinar section of our website later. If anybody wants to come back and refer to it or share it with anybody else, we will have that. So with that being said, let's jump into it. So first off, we're gonna just go ahead and start with a little bit of a discussion here. So we're talking about, today we're talking about steel studs, and a lot of our discussion is really going to hinge around like load-bearing steel studs or heavier gauge steel studs, not always used in load-bearing situations. There's many times where you might use heavier gauge studs even if it's not load-bearing. But when you're looking for specifically acoustical test data for steel studs, where do you go to look for that test data? Curious what kind of resources people are using to get this data these days. So anybody want to chime in? Feel free, and if not, Ben and I will talk about some normal resources we've seen, typical resources we've seen.
Canada National Research Council.
Yeah. So for any of you that aren't familiar, the NRC, the National Research Council of Canada, they've done a lot of big test series. And one of the nice things about their test series is they will test a lot of things back to back in their lab. So they control a lot of variables. They're more sort of scientific approaches to testing than a lot of times you will get where people will kind of test just different assemblies. But in the NRC's data, they'll take the same assembly and they'll kind of change one little variable. And they've done stuff with just like changing the screw spacing of how the gypsum board is attached. And so you can learn a lot more about effects of little variables. But one caution with that is a lot of that data is fairly old. And so, you know, materials have changed. You know, there's, at least in the NRC data I'm familiar with, there are very few like steel EQ gauge studs, right? Because that's a relatively newer development, at least more recently become more prominent in the marketplace. And so there's less data for that. And you know, some of those things, gypsum board has changed over the many decades since some of those reports were done. But that, yeah, that's a great resource.
What do you consider old data, and how should we look at data through the years?
Yeah, Ben, I'm gonna let you take that one because I
Yeah.
know that's something you've looked into a lot and thought a lot about with the Gypsum
Yeah.
Association in particular.
Yeah. So the ICC building code body published the G2 2010 guideline for acoustics. And in that guideline, the ICC said 20 years. After 20 years, tests should be no longer applied as acceptable references for test data. The GA 600 Fire Resistance and Sound Design Manual, at the GA, it's determined that 30 years is when they'll archive an assembly or archive a sound test. Like the GA will stop putting a sound test on the assembly design after 30 years if they haven't retested it. So after 30 years, they'll be like, hey, do you want to retest this design? And then they can either retest it or they'll archive the sound test.
Yeah.
20 and 30 years sounds like a long time. Do you agree with that? What do you think?
I think 20 years is, I don't know. It depends. I think that in recent times, 6 months seems like not long enough. Honestly, sometimes with all the changes in steel, like I think it depends on the assembly and on the material. Like for steel framing, you know, I see different like indications or stud gauge and mill thickness variations from like last year to this year in the steel industry.
Especially for EQ studs. I don't have the slide in here, but in one of Ben's past ASA presentations, he had a slide where he looked at the mill thickness for different like EQ studs. And so like a 25 gauge EQ stud or a 20 gauge EQ stud from the same manufacturer like changed from year to year. So they're, you know, as they're continuing to revise those manufacturing processes and go through their engineering and product development, like those studs might change from year to year. Whereas if you have a structural 20 gauge stud, that's 33 mil, like that's pretty standardized and specified in terms of its strength properties and things like that. So that might change a lot less from year to year. But some of these proprietary EQ studs might change significantly from year to year. So it depends on the products, I think, that are used in the test. And also, you know, I think it's important to keep tabs of the test standards and how those test standards have changed. You know, like right now, especially, we're in a period of making significant changes to a lot of the test standards. And some of them is just kind of reorganizing and things, but some of them is changing how we do background sound level corrections. It's changing how we do, you know, our reverb or our decay times and things like that. And as we make more of those changes, you know, like the results from older tests will not necessarily, you know, that introduces more variability when you're comparing tests. I see somebody's got a hand. Feel free to just unmute and jump in.
Hi. First thing, we all know that change is here to stay, and you have to take the lab reports with a grain of salt depending on who your contractor is.
Yep.
The field results may or may not, let's say your mileage may vary, okay?
Well, that's a Neil. Thank you, because that's a great intro to the rest of the that caution is a great intro to the rest of the discussion. So, I think we'll. Somebody go ahead.
Yeah, this is Alan. Hey, so I think what's important in reference to those dated tests is that the architects and designers and whoever is putting out the information, that what you are specifying is what you are getting in your submittals and what's being built out in the field. Because regardless, you know, then at least you have an apples to apples comparison as opposed to something changed. So it's important to really look over your submittals and make sure your mill thickness is the same and things like that to make sure that it's going to match the test that you have.
Yeah, and there's some challenges with that, especially with delegated design, and we'll get into that as we get going. So this is great, like awesome conversation. I see Steve Pettyjohn's got a hand raised too.
Sorry, I wanted to also point out in the chat, like Matt Golden mentioned that, and he's right about this. Matt Golden mentioned that in the ICC, in the original draft of the ICC G2 2010 document, it was actually originally 10 years. And then they changed it, and then I think somebody had requested 30 years, and then I think there was like a compromise, and they changed it to 20 years. So, yeah, originally it was shorter in the ICC
Money talks.
document.
Hey, so this is Steve. I was talking with one of the NRC testers at an ASA meeting, and I asked him how long we should do, and he said 5 years. Anything over 5 years, don't believe it. Because there are too many variations.
Right.
Yeah.
I would agree with that, actually. we retest all the time. I'm constantly retesting stuff.
Yeah, and yeah, and that's one of the reasons why, you know, we like working with Ben and PABCO, and you know, a lot of the data in here that you'll see that we'll talk about, it comes from Ben and PABCO because they do a lot of testing. And I see, you know, other people wrote in for other resources, Plytech Echo 1, which we talked about, NRC test data, USG wall selector, and the PABCO website. And the thing I would say about PABCO too is, I know PABCO's got some test data on their website. I know for a fact that Ben has way more test data than just what's on their website. So, you know, they're a great resource to reach out to. So, thanks everybody for all the input. We'll keep going. We'll have more questions and more opportunities to chime in too. So, one of the things that actually wasn't mentioned, I kind of expected people to mention. I think it's used a lot more by architects than acousticians, and I think a lot of the people I see responding are acousticians. But the Gypsum Association, you know, fire resistance design manual for sound control. I think the title has changed slightly. It's less of a mouthful now than that. But
yeah.
So this is a resource, like when I was consulting for a long time, a lot of the architects here in Portland especially like use this a lot. And I think that there are some regional variations in terms of how much architects refer to this. In Portland, it was really, really common. And it's, you know, it's a great resource in that it combines acoustics and fire, which is a really important thing. And Ben and I won't go on a rant about that today probably, but there's a lot of important stuff to pay attention to with that. But in here, in the older versions of this, so this is going back to the 2009 version, this is often the way that an assembly was listed. And it would just say 3 5/8 steel studs, 24 inches on center. But it didn't specify actually what the steel studs were, mill thickness or anything like that. There was just a note at the beginning of the book that said metal studs and runners are nominal 25 gauge unless otherwise specified. And I saw a lot of times architects, people would get into trouble with this. They'd miss that note and they would use an assembly like this as a reference for, you know, a load-bearing steel stud assembly or one that was heavier gauge for whatever reason, right? So in later versions of this, they have changed this. And I think I want to give Ben credit here because after 2009, Ben joined, and then the next version of this has changed. And so if you look at the new editions of the GA manual, you will see that all of the steel stud ones list a mill thickness specifically. And we'll talk more about why mill thickness matters versus gauge. If you're using this, get a new edition because it's way better. Yeah. Like they've worked hard to address that, and Ben's been a big part of pushing that.
Well, I also want to the everybody viewing, I wanted to point out like as well, like you can, if there's, we're always looking, we ever since after 2009, we've been trying to like improve both the explanatory notes section of the GA manual in terms of sound control, and then also just the design and everything. So if you have any feedback, let me know, or let us know, or let somebody at the GA know. We're always open to kind of you know, discuss, you know, how to do this in a way that helps the industry.
Yeah.
So yeah.
Yeah, so definitely check for a newer version of this. So when we're getting into, you know, stud gauge and mill thickness, right? So it used to be, and still a lot of times we talk about studs in terms of gauge, right? Which is the thickness of the steel, the metal that makes up the stud. The steel stud industry moved away from using gauge a long time ago, and they have moved to using mill thickness. And we have some folks on here I know from the steel stud and the steel cold form steel industry. So maybe somebody can put in the chat or chime in of exactly when that transition happened. But what you see here on the screen for this size is typically what you'll see for actually like the specification of studs. So that'll give, you know, the width of the stud, and then your flange width, that's like the side that the gypsum board gets attached to, and then your mill thickness. And so especially with EQ studs, which are like an equivalent gauge, so there's studs that by the process of forming the steel, they'll have like dimples and stamps, and maybe it'll be a higher strength steel, something like that. And so you can get more strength out of a thinner steel, and you can get the equivalent of, equivalent strength of a 25 gauge stud, which would normally be 18 mil, and you can get that strength with like 15 mil thick steel. So if you just say 25 gauge, that leaves a lot open to interpretation of what the actual mil thickness is of that steel. So we talk in terms of mil thicknesses now.
Also, I'll add that when you do an equivalent gauge stud, you have to use a higher yield strength steel often, and that may also affect the performance.
Yeah,
as
that
well.
can affect the acoustics,
Yeah.
right? So in this, so this is like a load-bearing wall stud schedule, right? So, one of the things oftentimes, like when we're specifying, wall assemblies, right? We're doing an acoustical report. Like if I'm a consultant and I'm doing an acoustical report, or we're looking at design details from an architect for walls, typically have one typical wall design for like a demising wall between apartments, or, between hotel rooms or something like that, right? But here's a load-bearing wall stud schedule, and you can see that like the mil thickness, so the spacing on these is the same. In this particular instance, the spacing doesn't change, but the mil thickness changes. Also, the flange width changes, and here we're really talking about spacing and mil thickness. But I think, Ben, you've done or are gonna do testing on flange width.
Yeah,
variation too,
like,
right?
In the next couple of weeks, we're going to be testing some designs that have different flange widths to see what the difference is.
Yeah. And so the point here, the idea is to point out that like even within a given project and within a given wall type, right? So like an interior or a demising wall between two units, you can get some significant variability in your walls just as they go up from floor to floor, and they're carrying less load as you go higher up in floors. So you can't necessarily just specify one wall design or get one test report that represents all of the walls, because there's these variables in here, and we'll talk about how much those variables matter. So that's for load-bearing walls, but even if you have non-load bearing walls, you're not always going to wind up with, a 18 mil 25 gauge stud or like a 25 gauge EQ, these like non-load bearing studs. So here's an example specification. This is for a high-rise condo project. So it was concrete, like PT slabs. So all the steel frame walls were non-load bearing, but you can still see that the typical wall was a base steel thickness of 33 mils. So that's like a structural 20 gauge steel stud. And then when the walls are supporting stone tiles, large format tiles, or like large porcelain tiles, then it was actually a minimum metal thickness of 54 mils. Again, non-load bearing, right? And these aren't like crazy tall walls. This isn't a 30-foot high wall or something like that, like for a movie theater or something. This is just like, this is their standard to have stronger, sturdier walls. And in the case of the tile, I imagine that the reason for the stiffer studs was to minimize deflection, which would minimize cracking for the tile and things like that, right? So if somebody pushes on the wall, it doesn't deflect too much where it's going to cause cracking of the tile. So you can't just assume that because you've got a steel stud wall that's non-load bearing that you're going to get those lighter gauge steel studs. So there's also, I was talking to a consultant a while back, and they did a lot of AV design work, and they had some for a display mount, the back box that mounted inside the wall cavity, mounted to the studs, was the actual like structural support that the display hung off of. And so that back box, the specifications for it said that it had to be 16 gauge, 54 mil steel studs, minimum that it was attached to. So again, might be a typical office partition, non-load bearing, but you're going to wind up with much thicker studs there. So what happens acoustically, right? So maybe you're using an old version of the GA manual. You go and you look for a steel stud wall, and you see the note, or you miss the note and you don't think about it, and what it's based on is a 25 gauge 18 mil steel studs. But then it's actually, you've got that AV back box on there, and it actually requires 54 mil steel studs, right? So you get this big change in your acoustical performance, right? There's almost a 10-point difference. So that's a really significant change. Could take you from a wall that meets your design criteria to one that's well below it. So how do you specify a wall assembly in these, right? And especially like, you know, for architects or acousticians, you know, like as an acoustician, if you're going through and you're in earlier in like the schematic design process, or even in DD, where maybe you don't know what all the stud mill thicknesses are going to be, how are you dealing with that variability to try and make sure that you're addressing these potential changes in studs and how that might affect the acoustical performance? I'm curious to just open it up to some folks for discussion of how you're addressing that issue currently.
I imagine you can just assume a worst case scenario, and any benefit you get is just an improvement off of that.
Yeah, I mean that's certainly one way you could do it. But in that case, you know, like if your typical wall design is just like you would just, you know, maybe just attaching a layer of drywall to either side of an 18 mil, you know, non-load bearing steel stud is sufficient to get your rating, like maybe for a, you know, basic office partition or something like that, right? But then if you assume worst case, like what is your worst case? Is it, you know, is it 54 mils 16 gauge? Is it 97 mil 12 gauge? Like, you know, is it 24 inches on center, 16 inches on center, 12 inches on center? And you're going to wind up, you know, with 2 or 3 layers of drywall on each side in order to get your rating. So you might wind up overbuilding in that case. If you're trying to take, you know, a more typical approach of just attaching drywall to it. Any other things? I know on some projects when I was a consultant, we gave multiple options. So we would give 2 different design options. We would give one if it was light gauge steel studs and another one if it was heavy gauge steel studs. So that, you know, ideally as the project progressed and the steel studs were, you know, more tightly specified, then they could pick whichever wall design applied to what studs they had. There was one large project where that did not work out because that change in design did not get caught. And so then they had an issue. So, you know, sometimes that can be helpful, but if it's not understood by the whole design team, or if it gets missed, then it can cause issues down the line. I see somebody's got a hand.
Yeah, Mike, Don Allen here. A minute
Hey,
ago
Don.
you said you had one design for light gauge and one design for heavy gauge. So what's the difference?
So in that particular case, so we had a, you know, and this is before I had, you know, talked to you in particular.
And you know with me, what's the difference between light gauge and heavy gauge?
Well, that's what I was just about to get into. So for those of you who don't know, Don has been in this. He's one of the folks I referenced. He's been in the steel stud industry for a long time. He's just newly started a new gig as the executive director for SFI, what is it? Steel Framing Institute of America. Is that right?
Steel Framing Industry Association. Yes. Industry
Association. Okay. So, you know, Don knows what he's asking about when he asks me these questions. So in that case, I think light gauge was 25 gauge and heavy gauge was like 20 gauge. I think that's what we had based it off of. So it would have been, you know, 18 mil and 30 or 33 mil.
Yeah, and the reason I stopped you here is that's what a lot of people say. Someone will say, "Hey, I specified light gauge. That means this." It's like, well, where in industry documents does it say that means this? And that's why our industry has moved away from using gauge, is because it means so many different things to so many different people.
Yeah, and while I got you, at what point did the industry move away from using gauge and to using mill thickness?
So it started probably around 2000 and is still in progress. Most contractors you talk to, everybody's going to still say gauge. You look at a sample of 10 specs and 5 of them are still going to say gauge. So probably even more. So it's an ongoing battle.
Okay. So it's still a long process of kind of retraining people to use that. But in terms of like official documentation and things like that, it's been quite a while that mill thickness has been the way that steel studs are referred to. Yeah.
Correct.
Yeah. So, and in that particular project, in a lot of cases for the light gauge, the 25 gauge 18 mil, it was direct attached gypsum board, and for the heavy gauge, we had resilient channel on those walls.
And really, in the industry documents, it's structural and non-structural. So structural is 33 mil and thicker. Non-structural is everything less than 33 mil.
Everything's less than that, right? But acoustically, it doesn't. Those breakpoints don't line up, right? And that's where we're going to kind of get into here. So start kind of talking about some data with this variation here. So this is all test data that Ben has done previously, and Ben's presented on this in the past, as have I with Ben. So here you see the variability. So the red lines are a single layer of 5/8 Type X drywall directly attached to the studs on either side. The blue are 2 layers of 5/8 Type X. And Ben, jump in and correct me if I'm wrong on any of these details. 2 layers of 5/8 Type X directly attached on either side. And then the green is resilient channel, and specifically RC Deluxe on one side, and then gypsum board directly attached on the other. So you can see
also the attachment of all of these matched what's required for fire design. So it was I think in this case it was screws attached to 8-inch at the perimeter and 12 inches in the OC in the field.
Or just 12 inches when attached to the resilient channel, probably, right?
Right. Yes. Yeah. That's right. That's right.
Yeah. So you see with the direct attached gypsum board on a 25 gauge EQ, which in this case was 15 mil, it was an SDC 49, and the worst case was an SDC 40, and that was on the 54 mil studs, right? So we see a 9-point variation, right? So this is huge variation, just changing the mil thickness of the steel, right? And you can see even just going from 54 mil to 43 mil, like there's a big change there, right? There's a ton of variability in here. And you can kind of, you can see some trends to it too. And then when you add resilient channel, you go from a high of 51 to a low of 47. So in this case, the resilient channel, adding that isolation did reduce the variability. But if you're thinking about a code minimum like SDC 50 requirement for demising walls, that variability still breaks across your code minimum, right? So your sort of non-structural framing achieves the code minimum, but your structural framing doesn't, right? So that could be a place where you could get yourself into trouble. Then if we go to studs 16 inches on center, you can see all the bars drop down, right? And so we go from a high of SDC 43 for the direct attached to a low of SDC 38. So that's a 5-point difference. So less variability than with the 24 OC. And then with RC, we go from 51 to 46. So in this case, the RC didn't actually reduce the variability either. It raised the overall ratings, but it still didn't reduce the variability. So we kind of wanted to look a little bit more at the data, where the variability was coming from, what was going on with these walls, look at it in terms of 3rd octave band data to really learn more about what's happening here. And then looking at this, trying to test, so typically when we're using, PAC products, we're using sound isolation clips and things like that. It's typically on, structural steel walls, 20 gauge and heavier. So we really focused in on like the 33 mil and the 54 mil because the 33 mil tended to get the best results from the the structural steel studs, and the 54 mil for whatever reason tended to get some of the lower results, especially with like the direct attached and even with the RC. Wanted to look into more detail of how do you address this variability, right? So if you've got a building like this, you've got load bearing steel studs, your stud spacing or mill thickness might change on every floor, right? Do you have to, what's changing that, and how can we maybe reduce that variability to make it easier to specify a wall that's going to meet your acoustical performance criteria? So Ben, I'll let you talk about this data since these are your graphs and this is your data.
Okay, so yeah, and Don, I wanted to point out too, we need to, Mike and I and whoever else is on the call that's involved in ASTM need to do some work on this, but the ASTM E90 standard for testing sound and measuring sound transmission loss, and Annex A1 for reporting, it says to report the dimensions, including thickness or gauge, the spacing in the test opening, fastening conditions and stuff. So even ASTM E90 still doesn't mention mill thicknesses, it says gauge. So we have some work to do there too. But
all we have to do is
Marcus on here?
I don't. It'll be perfect.
Yeah, yeah. Just get rid of or gauge, just thickness. Yeah, Steve.
I have a quick question. I did this because on one project with metal studs, I also put in a surface density for the gypsum board, and I put in 2.3, which the contractor did not catch. Everybody was using 2.2, which obviously caused a lot of problems. So what kind of surface density are you assuming at this point on these also?
There is no like for gypsum wallboard, there's no there's no standardized surface density with tolerances like that. Like, surface density needs to be 2.2 plus or minus blah, blah, whatever. There's no, that I know of, there's no,
yeah, we've looked into that a lot for trying to redefine the ASTM test specimen for the reference specimen that's used for the E90 test. And yeah, we couldn't find like the tolerances for gypsum board surface density don't exist. But I think to also maybe get at another part of the point that you're maybe making, Steve, is for all of this testing, everything in here, in all of this testing, all of the stuff that Ben has done in the past, and all of the stuff that like PAC has done to build off of this, we all used PABCO's 5/8 flame curb type X gypsum board, and it was all just standard off-the-shelf gypsum board. So we've used the same product, and within their manufacturing process, like they have their own tolerances and things like that, which I don't know, they won't tell me, but they're tight, and that gypsum board doesn't change much. And if you go look at all of these test reports, it's all reported to, I think, the 100th of a pound. I think it's they were pointing out the 2 decimal points. So
I Steve, I believe like every manufacturer is going to have like pretty tight tolerances on their different product lines. But now that we have like lightweight gypsum added to the market and all sorts of other things, it would be difficult to come up with like a generic, gypsum wallboard panel weight, surface density. I think what you did is what you should do. You should specify, if you want something heavier, you should say this, well, it needs to meet a minimum surface density of, like you said, 2.3. And if it's not, then you can't use it, anyway. So I think that's a good idea, actually, specifying that for your project. I like that. I think that's great.
Yeah. I see McCall's got a hand up too, and then we'll keep going because I'm realizing we're already halfway into our hour too. So
I'll go back to this, Mike.
The tables you had before that showed, the STC rating of each thing with different stud gauges and multiple layers. The one that was the sets of 3 bars. Are those just like single tests, or are those averages of, all of the tests of that type, or what is that data set?
No, those were single tests, but they were chosen from, we've tested those specific walls multiple times, many of, especially the ones on 33 mil, 18 mil. So those were the median in the range of STC.
Okay, it wasn't like a statistical average or median. It was just one picked from the middle.
Yeah, one picked from the median. That's right.
Yeah.
Yeah.
Or
I wanted to use a single test report.
Yeah, and or ones that were within the same test series. So like the testing that PAC has done, which we'll get to in a little bit, was like, everything was done back to back. So like we kept, we built the frame, we made some changes to it, ran those tests, and then took that frame out, built another one with, different studs, ran the test again. So it's all within one test thing. And like when PAC, we went and did our tests with our clips, we even matched like the stud locations within the test opening that PABCO had done to try and control variables as much as possible. So there's a lot of that's gone into this test series.
Okay.
Yeah.
Sounds good. Thank you.
Yeah. Yep. So on this one, Ben, let me click over here. So, go ahead. One of the keys we saw was this low frequency stuff, which I'll let you talk about.
Right. So I'll go through these really quick, Mike. So so we did a bunch of tests, but here's the ones for just single layer type X gypsum wallboard on each side of steel studs. And these were all 3 5/8 inch wide steel studs with an 1 5/8 inch flange. So all the dimensions were all the same, but the steel mill thickness changed. And you can see the mill thickness on the y-axis down below, and then you see the frequencies on the x-axis, and then the z-axis is your, and the color code is your sound transmission loss. So the warmer colors like red, orange, yellow are higher sound transmission loss, and the cooler colors, purple, blue, whatever, are lower sound transmission loss. And what we found is that you have this variation. Along the mill thickness axis. So as you change the mill thickness, it does change overall, in general, change the sound transmission loss across the whole frequency range, but especially in those mid frequencies. But at both 16 and 24-inch on center. However, on 16-inch on center, we saw this weird thing going on in the low frequencies where when you change the mill thickness, your what we used to refer to as the mass air mass resonance, which doesn't really apply to this because we didn't change any of the panel distance or mass. So there's no other reason why that should be changing. And so there's some research, there's some newer papers that talk about a membrane resonance down in the lower frequencies, and I think that's what it is. It's a stiffness related membrane resonance down in those lower frequencies. And since your membrane is acoustically coupled to the framing, your framing will affect that membrane resonance as well.
Yeah.
So that's what we kind of figured was going on at the low frequencies on the 16OC, but it didn't occur on the 24OC. But then when you add a layer on each side, so you double the mass, you still see the same effect. On 24OC, we didn't experience any change, and then on 16OC, you did experience that change across the mill thickness.
Yeah, so you have variability between, variability with mill thickness, you have variability with stud spacing, and then also depending on your stud spacing, your variability with mill thickness changes, right? So there's all these interrelated factors that affect how much variability you have.
Right.
So then on RC.
On RC with these, and I want to specify anytime for these tests, I've done other tests with other different RC channels, but for these tests, the RC that was used was specifically RC Deluxe, which is a different beast than almost any other RC except for Semco's RCXD. It's different than all the other RCs that you'll test, from Philips, from whatever, RCXD and RC Deluxe perform differently. They're the higher performing RCs, and for RC Deluxe, it didn't matter what the mill thickness was, even on 16OC, and it actually didn't really even matter whether it was 16OC or 24OC. They both performed pretty similarly. So that was, we kind of looked at that and we're like, well, I guess when you decouple one side of the partition, your mill thickness matters less.
Yeah, it matters less. And so at low frequencies, we saw that, especially on the 16OC studs, that low frequency resonance doesn't really shift around. It kind of stays at the same frequency now when you add resilient channels. So that further indicates that it was some sort of panel stiffness effect, because we added this much less stiff item in the terms of the resilient channel, and you saw the reduction of that variability down there. But you do still see variability at the coincidence dip, right? You still this reduction, and that's starting to affect the SDC, overall SDC ratings more. And so if you look at just the overall SDC ratings for these assemblies, you still see a 4 or 5 point difference between the min and max SDC ratings with the various mill thicknesses. So,
Matt,
and this
Matt, did somebody raise their hand? I think somebody raised their hand, maybe.
Yeah, that was me, just to let you know that Matt had that question in the chat.
Yeah.
Real quick, are these graphs available in tabular form?
They can be, Neil.
Yeah.
Just email me, Neil.
Yeah, and Benjamin, it was the Dietrich RC Deluxe is what was used for all of this testing for the resilient channel.
Right. Yeah.
So this, so Ben had presented on this. Originally, he presented this data at ASA in San Diego many years back. And so, Ben and I had talked about this. And so when I saw this resilient channel data, especially when we started looking at that, I was like, okay, you decouple the gypsum board, you reduce the effect of that stiffness, but then you still have some effects at the coincidence dip, which Ben has also done testing on this with quiet rock, which of course has, provides significant gains there at the coincidence dip. But I was like, okay, well, what happens if we add clip to this? Because, we further decouple, we have more effective decoupling of the gypsum board from the steel studs. Do we get more reduction in variability? And also because the clips are very effective up at that coincidence dip as well. So started looking at kind of like, where are we going to do our testing and where are these sources of variability? And in the interest of time, I'm not going to spend a whole lot of time on these because we could spend a long time talking about these. But this is looking at the difference between resilient channel and this direct attached gypsum board. And you can see here at the low frequencies, like at really low frequencies, this like purple over here is actually a reduction in the TL values. So at these really low frequencies, adding the resilient channel actually reduced the TL. It's outside the frequency range for the STC calculation, so it's not necessarily affecting the STC ratings, but you do have these really interesting low frequency effects going on. And then you can see there's also, variation in the effect of the resilient channel based on stud mill thickness too, right? So you don't get a consistent delta here, right? And so, again, looking at this data and the overall STC ratings for PAX testing, we decided to kind of focus on the 33 mil and 54 mil steel studs. So we were thinking about like the decoupling that clips provide, but the other thing we've talked a lot about, as Ben and I have gone through this data, is also the contact area, the connection points, right? If you're thinking about like energy transfer from one side of the wall to the other. So if you have direct attached gypsum board, right, kind of the red highlighted areas are your contact areas, right? So if you have your studs at 24 inches on center, here's your contact area, and you go to 16, here's your contact area, right? So it increases dramatically. I haven't actually like measured out the area and figured out what the change is here, but it's clear from the picture that it's a significant increase in that contact area. So you've got more area to transmit that acoustic energy from one side of the wall to the other. When you go to resilient channel, you no longer have that sort of like line or area connection. You have a point connection, right? And it's at any point where the resilient channel crosses the studs. And in a RC wall, you have to fasten the RC at every stud, right? That's required for fire. That's typical construction practice. So this is the actual like layout for the test wall. We did all this tests at North Orbit. So this is the actual like stud and RC layout for those tests. So with the studs at 24 inches on center and the RC at 24 inches on center, which I think in all of these, the channels were at 24 inches on center as their kind of standard spacing, you have 35 contact points. But you increase the number of studs when you go to 16 OC spacing, right? And so you increase the number of contact points. So it goes 50 contact points. That's a 43% increase in the number of contact points, right? So that's more contacts to transmit that energy. So we're thinking like, maybe that's another part of what's going on. That's another source of the variability, and especially maybe a source of the variability at those higher frequencies, like around the coincidence dip, where we still, even with RC, saw some variation with mill thickness. Whereas with clips, right, we're not attaching at every point where the channel, in this case, the hat channel, crosses the studs, right? So we have fewer connection points, which is good for less energy transfer. But also we keep the clip spacing essentially the same. It's 2 foot by 4 foot here. And so when you go to 16 OC studs, you only gain one contact point, right? So it's 22 at 24 OC and it's 23 at 16 OC. So it's only a 5% increase, right? So you get a much smaller increase in those contact areas. So we figured, hey, that might also be a factor that reduces this variability. So like adding clips increases the effectiveness of your isolation, the decoupling of the gypsum board from the stiffness of that steel frame, and it also reduces the variability in contact points, and so energy transfer through. So we figured clips might be an effective means of reducing this variability with stud mill thickness and spacing. But we wanted to actually go test it. So we tested two things. So on the right is our RSIC-1. It's a rubber isolator with a steel claw that holds the hat channel. And then we also have our RSIC-V, which is just the steel claw, which without the rubber isolator in there, you might not expect it to work that well, but it actually does work surprisingly well. And we've got a bunch of test data in here to substantiate that. So this is where we kind of get into like this partnership of testing, right? So Ben and PABCO had gone back and done a lot of this other testing, right, that I had been looking at. And I wanted to build off of that. So in order to do that, like we worked together. So PABCO supplied the gypsum board for the testing so that we could use the same gypsum board. And I also worked a lot with Ben and the test lab to coordinate to make sure that we controlled those construction variables, like where the steel studs were within the test opening, the screw spacing that they used to attach the gypsum board to the steel studs, you know, the resilient channel, confirming that he had used RC Deluxe, all of these different things, made sure that we could control those variables and work together to help bring all of this research together to help people out. So we'll go in and we'll first kind of look at like the effect of the different clips versus RC and the direct attached gypsum board, because you can see interesting things here about like what's going on at the different frequency ranges. So first thing is at the coincidence dip, right, as we add isolation, we see these big improvements in this, right? So the direct attached has this very pronounced coincidence dip. You add RC, you bump that up some. The RSIC-V bumps it up even further. And then the RSIC-1, you see this really big gain there. And then this is for 33 mil steel studs at 24 inches on center. And here at the low frequencies, you can see things are like fairly clustered together. You can still see a little bit of a shift of that kind of low frequency resonance. It shifts maybe like a third octave band between the direct attached to like the RSIC-1. And you see, you know, gains at those low frequencies. But when you go to the 16 OC, you still see these big jumps at the coincidence dip, but you also see much bigger shifts at the low frequencies. And it was the 16 OC studs where we saw that big variation with the direct attached gypsum board based on your mill thickness, right? And so here we see these shifting, right? So we're seeing the effect of the reduction in stiffness basically as we add these isolators. Ben, is there anything on these that like stands out to you or anything else you want to comment on?
Yeah, well, so in the case of the RC Deluxe, which is like the best RC, one of the best RCs you can get, there was a much bigger difference if you go down to like the 80 hertz, like 63 hertz, 80 hertz, 100 hertz region. There was this much bigger drop in performance, like up to 7, sometimes 8 dB drop in performance. And you don't see that as much with the sound isolation clip. The sound isolation clip gives you that like boosted performance, but then without the drastic drop in performance at those lower frequencies. You do drop a little bit because you're dropping that membrane resonance down to the 63 hertz, 80 hertz bandwidth, but it's still not that bad.
Yeah, it's not that bad, and something that, you know, these are all a single layer of JIP on each side too. So if you add another layer of JIP, you're gonna, with that adding that mask, you can shift that down further. You can improve your results down there too. But you see like this significant difference. I mean, like at 100 hertz, adding the clips gave you a 10 plus dB change, right? Versus the direct, or even really the resilient channel, it's probably like a 7 or 8 dB change. So you're seeing these significant improvements at the very low frequency TLs, which are often the hardest things. And that's usually what controls your STC rating and also what controls really your perceived sound transmission to the other side, especially when you have much higher isolation at these other frequencies. So you're seeing, you know, that shift down, and you're seeing an improvement in the transmission loss values and a significant improvement in the transmission loss values all the way across the entire frequency range. It's not like you're just getting improvements at like one kind of area, you're getting it across the entire spectrum just about, except for the very low frequencies. So then here's the heavier 54 mil steel studs at 24 inches on center. And you can see here that, you know, again, we see these big changes at the coincidence dip. But here then at the low frequencies, you see the RC didn't really change things much over the direct attached gypsum board. But then when you add the clips, you do see these bigger improvements at, you know, 100 hertz. You see smaller gains versus the 16 OC, but you still are seeing improvements at the low frequencies where you don't see differences with RC. And then when you go to the 16 OC, again, we see these big changes at low frequencies. Right. And so, you know, you see these changes of the coincidence dip, but you also really see this dramatic shift where that resonance really shifts like a third octave band down. And you can see these big changes between the clips and the resilient channel, where you get big gains in those performance, those TL values, even down to very low frequencies. So that's kind of looking at comparing the different kinds of gypsum attachment methods. But the other way to look at this is, so how much variability do we get with stud mill thickness and spacing? So here we've controlled for the attachment method, and we're changing mill thickness and stud spacing. So this is direct attached gypsum board, and you can see, there's some variation kind of across the entire frequency range, but like at 125 hertz, you see these huge changes, right? With mill thickness and stud spacing, right? When you go to resilient channel, that variation reduces, right? But you can still see, like especially the 54 mil at 1600C is just way worse at these lower frequencies. So you still have this variability, and it's, again, it's sort of broadband variability. When you go to the RSIC-V, you see things get way tighter all the way across. You still see some variation at the higher frequencies, but at these low and mid frequencies, there's very little variation here. And this is really kind of starting to get within like rebuild reproducibility range for these. And then with the RSIC-1, yet again, you see everything is really tightly clustered here for a large part of the frequency range, and a lot of the frequency range that really matters. So using the clips, both probably in terms of isolation efficiency, but also like contact points, dramatically reduces that variability. So what assembly do you use if you want to reduce that variability? So if you think about a load bearing steel stud building like this, and you're changing stud spacing and or gauge mill thickness as you go up, and you want to have one wall design that gives you consistent results, well, using clips does that. Like you can see in terms of the TL data, like the specific third octave band transmission loss data, you get very consistent results. But also in terms of the overall SDC ratings, kind of regardless of spacing or mill thickness, you essentially get the same result. There's like a 1-point variation, but it really came down to tenths of a dB variation at like 125 hertz, where it was 8 dB limited. So you see this much more consistent results. So it's a way of simplifying your design specifications, assuring more consistent results. And we haven't talked about it much in here, but as I've been talking to different people about cold form steel framing projects like this, one of the things that comes up more and more is a lot of these designs are doing delegated design for the steel studs. So that means like the architect will specify a wall width, specify that it's steel studs, maybe they'll specify a UL design and some acoustical performance criteria, but they don't actually specify the studs themselves. And that's often left in a delegated design for steel framing, that's left to the contractor. And a lot of the big steel framing contractors have in-house engineers that will, do the calcs and figure out what studs need to be used. So you might not know the final stud selection until well on into the project process. So you oftentimes may not have the opportunity to really dig into that and come up with, prescriptive designs that work for that particular steel stud wall. We have just a little bit after this, but I'll open it up to any questions here, or Ben, any comments that you have. I see we've got at least one hand from Neil, maybe some others too. Neil, you want to go ahead and chime in? I see somebody else has a hand up too.
Real quick, you mentioned that the architects sometimes specify the thickness of the partition. I had a project for a classroom preschool where, in order to meet the requirements for the square area for the classroom space, we couldn't add a clip or an extra layer of drywall. That is something that, space planning is the easiest acoustics, I always say, and sometimes the architects don't take that into account.
Yeah, there's always a limit to how much you can do, right? But I think like in this case, my hope is that like early on in a project, right, if you can have this conversation with architects, and I've been having it with a lot of architects, that like there is this variability and significant variability in steel stud performance, And if you plan early on for a footprint to include clips, right, that gives you that assurance of getting the kind of the results that you want, kind of takes a lot of the variability of the steel studs away, and make sure that you've got space to do that. And usually people aren't going to argue with you if you reduce the wall width, but increasing the wall width often adds a lot of headaches. I see somebody else. Dennis has a hand up.
Yeah, this is Dennis. Just an observation. There's so many variables that we're now getting into as you do all this testing. A lot of them, I suspect, have significant cost implications, which is something the consultant always faces. So how we select the criteria, what the cost implication is, how you're going to justify this when there are codes involved, and the design team is looking for certifications, going to get pretty complicated. Not to mention the cushioning, the consultant is looking for between the criteria and the known or expected actual performance in the field.
Mm-hmm. Yeah, and I think, with this, like, knowing the variability in the performance of steel studs, right? Like if the design team, like if the project documents call for a steel stud wall with gypsum board directly attached, right? Because the architect went and pulled that out of the GA manual, and it's 18 mil steel studs, and so then the project cost estimating is done based off of steel studs and a layer of drywall on each side. But then it comes back and it winds up needing to be 33 mil steel studs. I think Don Allen chimed in and said that tile TCNA requires 33 mil steel studs as the minimum for putting tile on a wall, right? So even if it's a short wall, typical construction, non-load bearing, but it's in a bathroom and you're going to put tile on the wall, right? You're going to be going to 33 mil steel studs, right? So you've got that variability in there. So if instead you use a more robust wall design with the RSIC clips, you take out a lot of that variability, and you've priced in an option that will work kind of regardless of what the steel studs are, that situation. And if you get into a wall where it is actually 18 mil steel studs at 24 inches on center, and it's going to perform well without clips, then like great, then you get to be the hero that comes in and says, hey, you can actually take the clips out of this wall and save money, right? Instead of being the bad guy that's like always adding cost at the end of the project where they haven't addressed it. Any other questions? We'll get on to one other thing. So one other thing that might come up is, what about double studs, right? So double studs is often a common way of providing high levels of sound isolation between spaces. So when we're talking about double studs, I'm talking about two completely separate sets of studs with like a 1-inch airspace and no like rigid connections between them, right? So here's a comparison that you might often make, right? So this is a RSIC-1 wall on the left. These are 3 5/8 inch 33 mil steel studs, 16 inches on center. And then on the right is same studs, 3 5/8, 33 mil, 16 inches on center, but double stud. So it does increase the performance. You get an STC 59 versus an STC 54, but you also have a much wider wall. You have twice as many studs, right? So what we want to do in all of this kind of testing, really, we've worked really hard to control variables, where there's a variable in this comparison that we haven't controlled, and that's the airspace between the studs, right? So first, if we look at this, we see that at some frequencies, right, they're very close in their TL, but at other frequencies down here, we're seeing some difference between these walls, right? And we figure this is maybe not a stiffness thing, but this is a mass thing, mass air mass thing because of the different airspace. But let's look at the stiffness thing first. So like I said, Ben does a ton of testing. So here's double stud walls, 33 mil, but also 54 mil and 15 mil, so a 25 gauge EQ. And you can see that the SDC ratings are all basically the same, but also the TL values are all very similar. But you do see at very low frequencies some variability here. And these were done all at North Orbit, same lab crew, all this kind of stuff. So typically at 50 hertz, I wouldn't put much stock into, few dB variations there. in this, we've got tighter controls, so maybe some of that variation is significant, but still very similar, right? So probably the difference between that RSIC-1 wall and the double stud is airspace, not stiffness or something like that, right? So let's then try to control for the airspace. So Ben just really recently, based on these conversations he and I have been having here, did 2.5 inch 33 mil steel studs at 16 inches on center. So that's a 6-inch airspace. With the RSIC clips and the 3 5/8 steel stud, you have a 5 1/4 inch airspace. So we're much closer. The double stud's still a little wider. Here we get the same STC rating, and if you look at the TL values, they're almost identical. At low frequencies, there is a little bit of variation there still, but like for the majority of the TL curve, like they're dead on. So really the clips are providing you that same level of isolation that you get with just completely separate studs. The difference between a more typical double stud wall and a clip wall is just that airspace. So if you're looking at using wider studs, a 6-inch stud or something like that, that increased airspace is going to give you better performance with the clips. And we do have some test data that shows you do get better results with like a 6-inch stud.
I was gonna add to this, Mike, to say that like I think that one of the biggest things that I've gotten from this is the back to the slide that you showed previously, like that, like we Mike and I have regular conversations talking about data and stuff like that, and talking about different phenomena, and some of this testing wouldn't have even come about without conversations with Mike and other people in the industry about different things like this. So I really think collaboration combined with taking some time and doing the work to do the testing and spending the money to do the testing, that it's just magical. We'll talk about stuff and I'm like, oh yeah, wait, I should totally test that. And so we added this like double stud series into a test series that we were already doing and did this testing, and now we have a comparison. So I mean, it's really, I think it's really good. I don't know, I just think it's really beneficial to the industry, even when we can collaborate. And
and
I agree. Two heads are better than one.
Yeah, two hands are always better than one. Yeah, and it informs the discussions that Ben and I then bring to ASTM and things like that too, as we're digging into these details. Like Ben just brought up, like we need to change what ASTM requires for the reporting in E90, so we take gauge out of it and stuff like that. So, and I know just as a parting thought here, and I'm happy to stay on for some discussion if folks want to. Ben and I have presented another webinar on this in the past. Before we had the clip test data, and we showed all the variability and things, and I got a response from a lot of consultants. They were like, dismay, right? Like, what do we do now? Like, you've thrown all of this like uncertainty at us, and now I don't know what to specify or how to do it or anything like that, right? And so part of it is like, we want to present this data to you so that you're better informed and you're aware of those things, and you can look out for those sources of variability and things that could catch you up on a project. But then I wanted to come back and present the clip test data, because my hope going into it was that the clips would be a way to significantly reduce that variability, and that panned out in the test data. So we've shown now that using RSIC clips, either the RSIC-1 or the RSIC-V, large part, dramatically reduces that variability. So you get really consistent STC results, but also like third octave band TL values too. And in this last little bit too, we've shown that double studs can do that as well. And there's certainly pros and cons to both of those. But we've shown for the same like wall footprint that the clips perform almost identical to a double stud wall. But like that double stud wall with 2.5-inch studs, you can't go as tall with it, right? You're going to have a lot more restrictions on your spans because they're such small studs. Whereas a 3 5/8 stud, you can go higher. And with the double stud wall, you don't get the structural benefit of having two studs unless you tie them together, and then you've eliminated all of the acoustical benefit that you had from double studs.
We've been there.
And we've tested that together too. So yeah. So I see a couple hands still raised. If anybody's got anything to chime in, that's the end of our presentation. But I'm happy to stick around and chat If anybody's got any questions, comments, concerns, other testing you'd like to see us do, any of that kind of stuff.
Hey, Mike, I just want to note in the chat, I put in a link to our assembly selector for the registration so people can get access to the test reports that we have published there.
Yeah, and it looks like what you put in was the login, not the registration. But if you go to the login, I think there's a thing at the top that says, click here to register if you're not registered.
Yeah.
So yeah, that we have, PAC has an online assembly selector where most of the data that I've presented here is there. I think the double stud stuff's not in there, but I think everything else is up there now. So if you register for that, you can go, and it's a database where you can sort and filter by assembly type, SDC or IIC rating. If it's a floor ceiling assembly, you can look for different UL designs, and you can access a lot of our different tested assemblies there. And you can go back and kind of look at this data and dig into it more if you're curious to do so. Yeah.
Mike Senior, I think, right, this is Mike at MD. You're muted. If you want to chime in, feel free to unmute yourself.
Oh, I just wanted to ask, he already answered my question when I raised my hand. I just wanted to ask about 6-inch studs and 8-inch studs and bigger conditions, and as well as will I be able to get this video so I can show the rest of my team this thing so they can learn all this stuff without having to be on live?
Absolutely.
Yeah. So we have, and maybe Mike or Steve, you can put it in here. So there's a webinars section of our website where we put all of the recordings of these webinars. So this one will be up there as soon as we get it downloaded from Teams and have a chance to get it uploaded. So that'll be there. And we do in our assembly selector in our database, we do have some wall tests with RSIC clips on, I think they're 14 gauge, which is 63 mil. 6-inch, I think it was 6-inch steel studs. I think they're 24 inches on center. I can't remember. So it was not part of a larger test series. It was for a particular project where they had 6-inch steel studs. They had some particular SDC rating they were going for, and it was a large enough project where it made sense for us, and we just went and tested it and got the results or exceeded the results that they were looking for. And so that's in there. So we don't have an apples to apples comparison with the exact same like mil thickness studs, but here again with this presentation, you can see that the mil thickness of the studs with the clips doesn't matter nearly as much. So you can kind of at least get a decent comparison kind of between the 6-inch and the 3 5/8 studs.
Mike, Jerry Lilly.
Hey, Jerry.
Do you have any data on, thinking back to the problem with the wall thickness, do you have any data with the RSIC-1 clips on 2.5-inch studs?
Yeah.
We do, I think. Yeah, I think that's in the database. I think we have 2.5-inch. I think they're 33 mil steel studs, aren't they, Mike?
Yeah, about 30 mil.
30
okay,
mil?
Good.
Okay.
2.5-inch, 30 mil. Yep.
Super, thanks.
Yeah. And the RSIC V, so like the RSIC V also reduces the wall thickness by like 1/2 inch, so it's not a huge difference over the RSIC-1, but it does slim the wall basically by almost like a layer of gypsum board. And it doesn't perform as well as the RSIC-1, you can see from this test data, but it's close. So that would be, if you're trying to thin a wall down and the RSIC V results are kind of where you need them to be, that's another option too. It's also less expensive than the RSIC-1, so it's a
good point.
Potential budget option. Anything else? I see somebody else has a hand. Dennis?
I think we covered Dennis's earlier.
Okay.
I think.
Correct.
Go ahead, Dennis.
Thanks.
Okay. John, did you want to chime in?
Sure. So regarding the non elastomeric one, the RSIC-5 or V.
Mm-hmm.
Yeah.
What's the hat channel gauge and thickness? And have you guys? Does that have stiffness requirements to it as well, or flexibility in the actual hat channel that's used in it? I suppose I would assume if you use a thicker hat channel in that versus a thinner hat channel, thinner gauge, that would have some performance difference. Do you guys have any data on that, or is there, or what was the gauge used in the testing that you did?
Yeah,
was it
so
just a 25 gauge, a light gauge hat channel?
Yeah, so all of the hat channel used in this testing and all of our testing is an 18 mil 25 gauge. And that is our requirement for our clips. Like that's what you have to use. If you try and put thicker hat channel in there, one, it's just a beast to try and get it into the clip, because like the point is that you squeeze the channel, you compress it so that it pops into the clip and then it springs back out, and that spring helps hold it in there. And also the 18 mil hat channel specifically, you can get with a hemmed edge. So it's this little, like it's the edge is rolled over. And that helps give the claw a little place to bite into, which increases the pull out load. So it's a requirement for our clips to use 18 mil hat channel. So that's always what you're going to see with any of our testing and with any of the installations of our clips. And I think that that's fairly consistent across other clip manufacturers as well, that it needs to be 18 mil. I don't know if Matt Golden is still on here, but if he has a difference in opinion, I'm sure he'll jump in and correct me.
I think the only clip that I've seen that has an allowable variation on the hat channel or furring channel is Kinetics with the rubber isolator, because it can hold a wider flange.
Yeah.
One of the other things is
the
that
attachment mechanism is different.
Yeah. The heavier gauge also typically doesn't, because it doesn't have the hemmed edge, it comes wider, so it actually creates more of a struggle.
Thanks, everybody, so much for joining us. Yeah, if you have any questions, feel free to reach out to either of us, me or Ben. Ben, do you have any other webinars or anything like that coming up that you want to promote, give a shout out for?
Nope, I don't.
All right. Well, we'll probably come back and do more. And if anybody has other topics that you'd like for us to cover, feel free to reach out. Like we enjoy doing these webinars. I always enjoy doing them with Ben. Yeah, if you've got any topics you'd like us to cover, reach out and we'll see what we can do. Thanks again, everybody, for sticking around. Thanks, Ben. Thanks for your time and all your test data.
Thanks, Mike.
And yeah, thanks everybody for joining us. Hope you have a great day.